radioactivity is not something that man created to be self-destructive. Radioactivity is natural, okay? It's organic, if you will. Not all natural things are beneficial or safe. It's a natural component of the environment. Humans and other living organisms have developed mechanisms to survive exposure to radioactivity. Some of the radiation we're exposed to comes from space, comes through the atmosphere. The atmosphere stops a lot of it, but some does get through. And there's also radiation that's just in the dirt around us. On the periodic table, all of the elements beyond atomic number 83 are unstable and radioactive. There are some isotopes of elements smaller than 83, smaller than bismuth, that are also unstable, but they have some stable isotopes. So half-life. Half-life is not just an exciting video game. Half-life is a concept from radioactive experiments. So radioactive nuclides decay at different rates. So some of them fall apart, they emit their radioactive particles very quickly, and some do it very, very slowly. What we call half-life is the time it takes for half of the parent nuclides in a radioactive sample to decay to the daughter nuclides. Each of those decay processes happens basically instantly. It's not like this alpha particle is moving and leaving in slow motion. It's bang, it decays and the alpha particle is emitted. But when you have a sample of this radioactive substance, you have gazillions of atoms, right? And they're not all decaying at the same time. Half-life is the time it takes for half of them to decay. And so this is a concept that you kind of have to work on to get your brain around. So you've got this compound, it's radioactive. In a certain period of time, half of them decay. In that next period of time, half of what's left decays. Not the other half of what was originally present. So it's not like in 2 half-lives, it's all gone. Instead, it gets cut in half at every half-life. So after 1 half-life, you have half of what you started with. After 2 half-lives, you have 1/2 of 1/2, or 1/4. And after 3 half-lives, you have half of that, which is 1/8. After 4 half-lives, you'd have 1/16 of what you started with. So nuclides that decay very quickly have short half-lives. They're very active. They have a lot of decay events per unit of time. A decay event is the emission of radiation by a single radioactive nuclide. We're looking at individual atoms here. A decay event is 1 atom decaying. So a substance with a short half-life is going to have a lot of decay events in a given amount of time. So radon-220 has a half-life of approximately 1 minute. So if you started out with 1 million radon-220 atoms, which really is not that many, after a minute you're going to have 500,000 left. After another minute you're going to have 1/4 of a million. After another minute, you'll only have 1/8 of a million of what you started with. Thorium-220 is much less active. Its half-life is longer. And so, if you start with 1 million and you want to get to 500,000, it's going to take a lot longer to get there. So here's us trying to explain this in pictures. So if each of these represents 1/10 of a million atoms, we start out with 1 million of these thorium-232 atoms. It has a half-life of 14 billion years. Is that longer than a minute? Yeah, it's a lot longer. This is an extremely long half-life. 1 minute is pretty short. So if you start out with 1 million, and then you wait 14 billion years, we're not going to do that in lecture today. At the end of 14 billion years, you'll have 500,000 particles left. With the radon 220, you're down to 500,000 after 1 minute. You wait another 14 billion years, now you're down to 2.5. Another 14 billion years, you're down to 1.25. You get the idea? So it just gets cut in half every half-life. Each different nuclide has its own half-life. And that half-life is not affected by chemical conditions or physical conditions around it. It just does what it does. The nuclides decay, and they decay according to their own schedule. They are not influenced by the outside. So there's nothing you can do to make the half-life faster or shorter. It just is what it is. Here's just an example. Thorium-232, we talked about that, the 14 billion years. That undergoes alpha decay. Uranium-238, 4.5 times 10 to the 9 years, so 4.5 billion years. Carbon-14, 5,730 years. Radon-220, 55.6 seconds. They rounded it up to a minute in the earlier slide. Thorium-219, so this is just a different isotope of thorium. This has a half-life of 1.06 times 10 to the minus 6 seconds. 1 microsecond. Half of it's gone. Okay, so how do you do problems with this kind of stuff? Here's an example. A radium-226 sample initially contains 0.112 moles. How much radium-226 is left in the sample after 6,400 years? The half-life of radium-226 is 1,600 years. So there are math ways you can do this. If that appeals to you, I know that you can figure that out, and so I'm not going to talk about it. We're going to talk about the less mathy way of doing it. So what we're going to do is we're going to take our sample. We had 0.112 moles. Okay, and so this is our, we'll call it N for the amount, and we'll call this T for time. So at time 0, that's what we've got. What we're going to do is we're just going to kind of count and divide. So 1 half-life is 1,600 years. So after 1,600 years, how much do I have left? Half. After 1 half-life, I have half. So I need to take my 0.112 and divide it in 2. So I'm going to divide by 2, 0.056 moles. Well, let's go another half-life. So what I'm doing over here is I'm adding 1,600, and what I'm doing over here is I'm dividing by 2. So I add 1,600, that'll give me 3,200 years. And then I have to divide that 0.056 by 2 again. 0.028 moles. Have I gotten to 6,400 years? No, let's just keep going. So I'm going to add another 1,600, so that's going to be 4,800 years. And I divide by 2 again, so that's going to be 0.14 moles. Each half-life, it gets cut in half. I add another 1,600. Oh, cool, I got to 6,400. So I divide this in half again, and there's my answer. After 6,400 years, that much is left. Any questions? Yes?
Sean had a good question. If you had the LR at 103 and you went through beta radiation, where would it go? Do we just make it do
If you had LR, okay, let's see, beta emission, it would go to 104. It would be, I think 104 is Rutherfordium, named after Rutherford.
So there are other elements besides.
Yeah, the elements that are listed up there that are just outlines, they do exist.
So it goes past 118.
Well, I don't know what the highest one currently is. They just added like four other elements. Those guys are all man-made. And so they make them by bombarding another atom and causing it to gain protons. And we'll talk about that in a minute too. And they're, yeah, you won't find those in nature. They're very, very unstable. Radioactive decay series. So where do these naturally radioactive elements come from? Well, some of them have very long half-lives. You know, like this 14 billion years. Okay, so some of that was present when the Earth began, however you think that happened, and it's still around because there hasn't been enough time for all of it to decay. Others are formed by other processes. So when you have the radioactive decay of one radioactive nuclide, it often forms another radioactive nuclide. Uranium, element number 22, is the heaviest naturally occurring element. Everything above that does not occur naturally. Uranium-238 will decay to thorium-234. That has a half-life of 4.47 billion years. That's going to hang around for a while. Thorium-234 is radioactive. It's going to decay to protactinium-234. That has a half-life of 24.1 days. So if you go out looking in the environment for these different radioactive nuclides, it's harder to find the protactinium-234 because it has such a short half-life, and it comes from something that has a very long half-life. Protactinium also is radioactive. It decays to uranium-234, it has a half-life of 244,000 years. So this goes through several steps, things going from one element to another, and they're all radioactive, and so they keep decaying. Eventually, it gets to lead-206. Lead-206 is stable. Once it gets there, it just stays lead. So the net result of this is all of the uranium-238 present in the atmosphere is slowly decaying away, and eventually it'll all turn into lead. There's a graph. You see, you start out up here, and it goes to this and this and this, and the different kinds of decay, and yeah, you end up with lead.